Hi students, hope you all are doing fine. So today we come with a new class, new video, okay, new set of ideas. Uh, Last class we discussed about electrostatic force and superposition principle, and then we continued doing problems, and I hope you are a little bit comfortable with the problems. Try to solve the home exercise problems. If you are not able to get, let me know the question numbers which you are not able to get. But before you directly ask me, try as much as possible. Hints also I have given, right? So try to solve, and if you are unable to get, then please let me know. I will help you out. Okay. Now, today we will be continuing with the few questions which are left from exam corner, entrance corner 2. And once we are done with this, we are going to start the concept of electric field. And I've told you before also, it is a very, very important concept. And I'm sure after this video, you will be able to understand the concept of electric field and also solve problems based on electric field. Okay, so let us continue the seventh question of entrance corner 2. So in the seventh question, entrance corner 2, in the seventh question, they have kept two charges along y-axis. Okay, so this is x-axis, this is y-axis, and they have kept one charge here q2 and one charge here q3. Okay, and they are seeing another charge q1 which is kept on negative x-axis. It feels a force F. Okay, this charge feels a force F because of these two. Okay, so that force is F. This is the force on q1 by q2 and q3. Now the question is, another charge capital Q, okay, is added on uh, Q is added at x comma 0. That means somewhere here, right? Because the y coordinate is 0. So somewhere here they have kept this charge. Then they are asking what will happen to the net force on this charge. Will it increase? Will it decrease? Okay, so let us solve this. Simple question. It is from NCERT exemplar. Okay. So let us see what is this F first. You know that this is the force on Q1 by Q2 and Q3, right? So Q2 will exert a force like this, right, along the line, joining the charges, and it will be repulsive. Similarly, Q3 will also exert force on Q1, repulsive, right? And the resultant of these two will be where? It will be along this direction. Of course, we are assuming that this magnitude of this and this are same. Okay. So here there will be a force F which they have given to be this. Now when you keep another charge here, okay, let me put this charge now here, then what will this capital Q do? Capital Q also they have mentioned positive only. So this capital Q will repel this Q1 with another force, F dash, let us call it. Where is the direction of F dash? In the same direction as this force. So that means the net force will be F dash plus F, which means the net force now increases. Okay, so the force will now increase when you add this capital Q here. Force on which charge? Q1. So which is the right option? Option A. Now think what would happen instead of adding capital Q, I add minus Q. Now if this is minus Q, then this F dash, okay, so already there was a force capital F, right, which is the net force on Q1 by Q2 and Q3. This they are given in the question. Now if you add minus Q, what will this minus Q do to this plus Q1? It will attract F dash. So since now this force is in opposite direction to the previous force, the net force will be F minus F dash, because F dash is in opposite direction. So adding minus Q here will make the net force here less. Okay, so the force now will decrease. So even without knowing the numerical value, we can decide whether the force on this Q1 will increase or decrease when this Q is added here. But in the question they added plus Q. But in exam they will always change the question slightly. So you should be able to solve it by knowing the concept. So let's see question number 8 now. So in the meantime, you can read the question. Okay, always have EPL with you. And let us now see question number 8. So question number 8 says the relative permittivity of water is 80. Relative permittivity of water is 80. They are asking what will be the permittivity. Permittivity of water. You know that permittivity is permittivity of vacuum into relative permittivity, right? How was relative permittivity defined? It was the ratio of permittivity of the medium by permittivity of vacuum. So if you cross multiply, you will get this. Now the value of this I mentioned in the first class. Okay, so this value is 8.85 into 10 power minus 12 into this is 80. So then if you solve this problem, you will get 7.083 into 10 to the power minus 10. Okay, 83 will come. Okay, fine. So like this you can easily solve. Unit of this will be same as this. This is unitless. This has no unit, but this two has unit, right? And what was the, by the way, while now I remembered, while solving the first question, when I was finding the unit of permittivity, the formula was 1 by 4 pi epsilon naught Q1 Q2 by R square, right? I by in excitement or maybe by mistake I wrote R. So that small mistakes you should not do in exam. So now if you want unit of epsilon naught, bring this epsilon naught this side, force will come this side. So unit will be Coulomb square by Newton meter square. Newton meter square. So this would be the answer, which is option A. Okay. Now let us see question number 9. Question number 9 can also be asked as a board question in the sense they may ask you what are the properties of electrostatic force. Okay, so properties of electrostatic force, the force between static charges. Okay, electrostatic force. So three properties, general properties we will be mentioning. Okay, so what are the three general properties? The first one, it obeys inverse square law. That means the force is inversely proportional to square of the distance, just like gravitational force was. So both gravitational force and Coulomb force, which is electrostatic force, is inversely proportional to square of the distance. So in that case we say it obeys inverse square law. Okay. Second, it is a central force. Central force. By central force I have already discussed with you in one of the video. If there are two charges Q1 Q2, the force between them, whether attractive or repulsive, will be always along the line joining the charges, will be always along the line joining the charges. So force on this will be repulsive if both are positive, and force on this will be repulsive if both are positive. Or it will be attractive like this, but it will be always along the line joining the charges. So in that case we call such forces central force. Third, that it is a conservative force. Now conservative force was discussed in first PU. So do you remember what is the meaning of conservative force? So conservative force is a force, the work done by such a force will be independent of the path. It only depends on the initial position and the final position. That is one way of saying. Another way of saying is the work done by electrostatic force in a closed path, in a what path? Closed path, will be 0, because it does not depend on path, right? It depends on initial and final. So if the path is closed, it means initial and final will be same, and then in that case work done will be 0. Now don't think all the forces in nature are are conservative force. Friction, for example, is not conservative force. However, gravitational force is conservative force. Electrostatic force is also conservative force. Detailed proof of this we will be discussing in second chapter. Okay. However, a little bit, let me give you feeling for why electrostatic force should be conservative force. Okay. So these three you note down. Now in question number 9, they have said first option is conservative force, correct. Second option is central force, correct. Third option is it obeys inverse square law, that is also correct. That means option D will be right, because option D says it has all the properties. So let me try to explain to you why uh, electrostatic force is conservative force. Okay, so imagine I have some charge plus q, small q, capital Q, whatever you want you can write. Okay, now imagine I move another charge q naught, okay, from this point to this point, like this way I move. Now you know that the force will act along the line joining the charges, right? So the force on this charge will be in the same direction. This is the force, and this red arrow represents the displacement, okay, from here to here. So what will be work done while going from 1 to 2? So from going to 1 to 2, work done will be force acting on this charge, which is repulsive because I took like charges, into displacement. Now you come back from 2 to 1. Now you come back from 2 to 1. Does the direction of force will change? No. Whether the charge is coming this way or that way, force will be repulsive because both are like charges. So force is still this side, but displacement is now this side, 180 degrees. So work done will be negative. Right? I hope you remember work done is force into displacement into cos of angle between force and displacement. And for small displacement, I can assume the force is constant. So imagine I have taken this displacement to be very small. So now if I calculate work done from 1 to 2 to 1, 1 to 2 to 1, then it will be this plus this, that will be how much? 0. So this in a simple way proves that electrostatic force is conservative force because work done to start from to move the charge q naught from 1 back to 1, okay, is 0. Now of course you may be thinking, sir, you took a very simple path. What if I take this kind of path, this one? Okay, I start like this and then I come like this back to here, then also you can show that the work done will be 0. However, this will take more time and that we have to do anyways in the next chapter. So let us not waste our time doing it now. Okay. By the way, if it is friction, okay, so imagine you have a block on a table. Okay, when you move the block from here to here, 1 to 2, friction will be which side? Friction will be this side. So displacement is this side, friction is opposite to the motion. So work done from 1 to 2 will be what? Minus force into displacement. Negative because the directions are opposite. So cos of 180. Cos of 180 is minus 1, right? Yeah, it's visible right now. Okay. Now let us say I bring the block now from 2 to 1. From 2 to 1. That means displacement will be this side now. Where will be friction? Friction will be again opposite. Not like this force. This force doesn't care where the body is moving. This force is repulsive if the charges are positive. This force is attractive if the charges are negative. It doesn't depend whether the body is going this way or that way. But friction depends on, kinetic friction depends on how the body is moving. So if body was going that way, friction was opposite. So work done was negative because cos 180 will come. Similarly, now when you come from 2 to 1, 2 to 1, again you can see displacement is this side, friction is opposite. Again it will be negative. So total work done from 1 to 2 back to 1 is not 0 now, it is minus 2 Fs. So in case of friction, you see that the work done in closed path 1 to 2 back to 1 is not 0. That is why friction is not a conservative force. Okay. Fine students, so we have completed the entrance corner and we have completed the problems of charges and Coulomb force and superposition principle. Before I start electric field chapter, one of my students has asked a doubt based on Coulomb's law. So usually I told you I will do doubts at the last, but since this is based on Coulomb's law and we are going to end this session and we are going to start next session, let me solve this doubt now itself. Okay, so let me explain the question first. So first understand the question. Okay, there are two small charged spheres q1, q2, and this is connected to a thread. This is a thread and this is also connected to a thread. Okay, so these are insulating threads. Insulating threads. Okay, and the values of the charges are given. Q1 is given 9 nanocoulomb. Q2 is given, sorry, uh, Q1 is given 2 microcoulomb. Q2 is given minus 2 microcoulomb. And this separation right now is L, and L is given 15 centimeter. The mass of both the balls are same. Mass is same, and mass is given how much gram? It is 40 grams. Question is, listen to the question. By how much this end, let us call this end O, let us call this end P. So question is, how much you should move this end up? Okay, H. So question is, what should be H? What should be H so that this ball, let us call this ball Q2, okay, so that ball with charge Q2 falls they are saying. Okay, so just pause the video and make note of the question. Okay, yeah, so once you have made note of the question, let us understand now how, what is this question. Looks little complicated, right, if you think. So now let us think carefully. First of all, this is a box which is hanging from some support. Okay, this is a support. Okay, you can think of it as some some bar is there like this. Okay, so some metal bar is there and the pendulum is hanging like this. So think of this like a pendulum. So I have no problem that this pendulum is standing like this, right, down. But why is this standing up? That is the question. Because this charge was positive and this charge was negative. They told minus 2 microcoulomb. So they will attract each other, right? So this ball actually may be lying somewhere here, but when this ball comes, it is attracted, right? So it tries to stay here. So right now this system is given like this. Since it is given like this, it means everything is at rest, matlab equilibrium. So let us apply our Newton's law. First, how to apply Newton's law? How to apply Newton's law? First, you have to choose the system and draw all the external forces acting on the system. So for this ball, Q1, what are the forces? One force will be mg, right? One force is mg. then this wire is connected, tension will be also there. Let us call this tension T1. And how to draw the direction of tension? Along the string away from the body. Tension always acts along the string away from the body. Okay. So this is the body, this is the string. So tension will act along the string away from the body. Because tension is a pulling force, right? So if you uh, take this, see, suppose some wall, and you take this body and you pull this body this side. Only if you pull, then the wire will be tight, right? Then tension will come. Now, if I ask show the tension force here, how will you show? It will be this way. So this is the tension on the block. Understood? So when you try to pull the block this side, this is your pull. Tension has to be this side. Otherwise, how this block is at rest? It will just come out, right? If your, by the way, if your pull is very high, then you know this block will come out because the wire will break. Otherwise, the tension here will balance your pull. So tension must be along the string away from the body. Okay. So now another force will be there. Is there any other force? Yes. This charge is Q2, this charge is Q1, and they are unlike charges. So there will be a electrostatic force. Attractive. Let me write this as Fe. Fe. It is visible, right? Fe. Okay. Now let us see forces on this. So there will be mg. Mg will be always Mother Earth always tries to bring us down. Okay, so Earth will pull this mass with force mg. Then this is the wire. So tension will be along the string away from the body. Just now I told along the string away from the body. So tension will be T2, let us say. And this is also attracted to this charge. And that force is your Fe. Electrostatic force between these two will be same, right? 1 by 4 pi epsilon naught q1 q2 by distance square. Okay. Now, since these two are in equilibrium right now, let us see, since it is in equilibrium, net force should be 0. Net force should be 0 means upward forces should balance downward forces. So for Q1, let us write Newton's second law. Upward force is T1, downward force is minus mg, and this is also minus Fe because these two are in opposite direction. This is the total force. But total force must be 0 because it is in equilibrium, which means I can take this to that side. So tension here is mg plus Fe. Q2, do the same thing for Q2. So upward force is Fe, and that will be balanced by downward forces. Mg plus T2. So what will be T2? Bring Mg this side. Fe minus Mg. Now observe carefully. Observe carefully. In the question they asked you how much this point should move so that this ball will fall. How much this should move up so that this ball should fall. Now when you move this up, what will happen to the electrostatic force? It will increase or decrease? It will decrease because you are increasing the distance. So when you move this up, electrostatic force will decrease. If this, did I do correctly here? T1, yeah. So if this decreases, still this will be positive only. So tension here will decrease, right? Tension here will decrease, right? Okay. So if this decreases, then this whole thing will decrease. Here, if this decreases, then this will also decrease, right? And if this decreases, see, this is decreasing when you take it up. But even if this is decreasing, it will start from some positive value and then decrease, right? So which one will become see, this will also decrease. So now the question is, as I keep this moving up, electrostatic force will decrease. If electrostatic force will decrease, then tension here will also decrease, tension here will also decrease. Question is, which tension will become 0 first? This one, because this is already lesser than this one. This is Fe minus Mg. Understood? So when Fe decreases, T2 will also decrease. And when T2 will be 0, tension here will be 0. Tension 0 means what? The wire is slack. Slack matlab loose. So if this wire becomes loose, what will happen if this wire becomes loose? The body will fall. Right? Otherwise, before, this electrostatic force was pulling it up, so there was still some tension. It was tight. But once the tension here becomes 0, this ball will fall. And if this becomes 0, what does it mean? Fe should be equal to mg. Once the body reaches here, this point reaches here. Okay, fine. So we understood the condition for this ball to fall. So for ball with charge Q2 to fall, what is the condition? This mg should equal Fe. Not right now, okay, when you take it here. Because the question was, here it was already in equilibrium. How much you should move so that this ball will fall. So once you move here, what was M? M was 40 grams. So 40 by 1000 kg. Convert everything in SI units. G value you can take 10. Electrostatic force is what formula? 1 by 4 pi epsilon naught. Q1 was 2 microcoulomb. Q2 was also 2 microcoulomb. Yes or no? Q2 was also 2 microcoulomb. Q2 was also 2 microcoulomb, right? Minus sign I am not writing because we are writing the magnitude divided by distance between them. Don't write L because right now it is not falling. When this point reaches here, now listen carefully. If this point goes up by h, this ball will also go up by h, right? Because this is the string, this is the ball. So if this point moves up, this ball will also go up same distance. So if the ball goes up h, what is the new distance? L plus h. So now new distance is L plus h whole square, right? Okay. So this will give you this 1 0 and 1 0 will cancel. This 0 and this 0 will also cancel. So this will be 4 by 10. This 4 will cancel with this 2. Right? So, and this, what was the value of 1 by 4 pi epsilon naught? Let us write here only. It was 9 into 10 to the power 9. So if you cross multiply, L plus h whole square will be 9 into 10 to the power 9 into 10 to the power minus 12, and this cross multiply into 10, which means this will become 10. So this will become 10 power 10 into 10 power minus 12 it is. That will be how much? 9 into 10 power minus 2 meter. So let us not write unit. Actually it will be meter square because this is distance square, right? So L plus h whole square. Now you take the square root. So L plus h will be square root of this will be what? 3 into 10 power minus 1 meter, which is 0.3 meter, which is 30 centimeter. And they are asking h. So h will be 30 minus this L. And L was given how much? 15 centimeter. So 30 minus 15 centimeter will be 15 centimeters. Okay, so this is the answer. So I hope all of you have understood. It's a very interesting question. You have made use of first PU concept and second PU concept. So like this, please enjoy the solution and think creatively and solve more and more problems. That way physics will be very interesting. Okay. So now students, we come to the concept of electric field. Okay, so let us write the name first. Electric field. First of all, the symbol we write is capital E and it is vector. So it is a vector quantity. 1 mark question in PU, second PU. Okay, fine. Now What is electric field? To understand what is electric field, think this. Till now what you know? You know if there is a charge q and there is a charge small q. I'm changing the symbols now. Before I wrote q1, q2, right? Capital Q, small q. Then this charge will feel a force because of this charge. This will also feel, of course, but let us say this is fixed. Then if you keep this charge here and you leave it, this charge will feel a force. And that force is given by what formula? 1 by 4 pi epsilon naught q by r square. When can you use this formula? When can you use this formula? If the charge here and here are point charges. Right? Okay. Now, what I don't like is this. Okay, so imagine, students, that you are standing here, you, and I'm standing here, me, and I say that you are able to apply force on me, like that, directly. Then how do you feel? How do you feel about that? Suppose I say you are able to push me. Push is a force, right, in physics? Push, pull. So if I say you are able to push me without any contact, see, there is no contact, there is no string, no string is connected, no spring is connected. So if I say you are able to push me without touching me, it looks very surprising. You feel like, sir, some magic is there, right? Like this I'm doing and you are moving. So that would be very surprising. So similarly, scientists have always found this also surprising. Understood? This is able to apply force on this without any contact. Of course, there is a name called non-contact force, but still, it is just a name, non-contact force. Instead of saying magic, if you say non-contact force, that doesn't mean you understood it, right? So, people did not like this concept that this charge is able to exert force on this charge directly, okay, without any process, without any mechanism by which the force can be transmitted from here to here. So people did not like this concept, and one of the person who tried to think about this was Faraday. So what Faraday said was like this. He said, when this charge is not there, when this charge is not there, this charge creates something in the surrounding space, something in the surrounding space. Okay, so something will be here when this charge is present in vacuum. Let us talk about vacuum right now. And that something was given the name electric field. Okay, so electric field basically is some region surrounding this charge, where if another charge will come, that charge will feel a force because of the electric field. So now I am not saying this charge applies force on this charge. I am saying this charge creates electric field, and that electric field will exert force on this charge. Okay. Now please listen, keep listening. Okay, don't get too confused right now. Just keep listening. Everything you will understand. Just keep listening. Now, let me first try to convince you that when this charge is present in this point, the surrounding space, we must have something which it did not have before. It must have something new. Let me try to prove it. Okay, so let us say this charge is not there. So now there is no charge. So what is this space? Empty space. So imagine Pankaj sir is walking in this empty space like this. He is walking like this. Okay, I'm showing you the head because I'm showing you top view. Okay, from here. So I'm walking like this. So there is nothing here. There is nothing here. My motion will be undisturbed. I can aram say walk. And what we will do? You take me and rub me on the wall nicely. So if you rub me, what will happen? I will acquire some charge. Now will it something will happen? No, nothing. This I have charge, right? So I will continue. Yes or no? Now think I keep a charge here. Okay, now I walk. Then what happens? Because of the presence of this charge, my motion will be deflected. I will be repelled. That means what? When this is present here, something happened to the space here, because of which I felt a force. Yes or no, students? If you are feeling a force, if this object is feeling a force, something must happen nearby, right? Something changes must have happened compared to before. See, when this charge was there, I was able to go aram se. So the space had no effect on me. But when this charge is present, the space has changed. And in what way it changed? Now we say because of the presence of this charge, it created everywhere electric field, and that electric field is responsible for me to feel the force if I have charge. So please don't think, though I cannot touch electric field, I cannot smell electric field, it is very much present. It is very much present. Okay, if that electric field was not there, I would have gone straight, remember. But because there is a charge, because of that electric field produced by this charge, I feel a force. Okay. So this is how the concept of electric field was introduced. I will tell you more things to convince you. Don't worry, okay? But keep listening. So how to define electric field in words, okay? In physical words, then you can say electric field due to a charge. Remember, electric field is always due to a charge. So electric field due to a charge is the region surrounding the charge, where if you keep another charge, it will feel a force. If you don't keep also, no problem, electric field will be there. See, it is like, suppose I put perfume, okay, and I stay somewhere, then what happens? That fragrance will be no around me, right? Now whether you will feel the fragrance or not, okay, that depends on whether you bring your nose and stand in that region where my smell is present or the fragrance is present, right? That whether you will feel that smell or not depends on you, whether your nose detector is brought or not. So whether another charge will feel force or not depends on whether you keep another charge or not, but that smell is still present. I don't need your nose for smell to be present, right? Once I have perfume in my body, there will be smell. Similarly, once there is charge in empty space, there will be electric field. There will be electric field. If you want to find force due to the electric field, then you have to put a charge. Okay, so this is one point I want you to please focus on, and that is how we define electric field. Later, after I give you the mathematical definition and few problems, I will convince you more nicely that electric field must be there. Without electric field, Einstein's theory of relativity will fail. Okay, so I will convince you, give me some time. Okay, so till now what you have learned about electric field, it is the region surrounding the source charge, where if you keep, see, the question is if you keep another charge, it will feel force. If you don't keep also, it doesn't matter. Okay, so one thing I think by now you have understood, and make a note: electric field is property of the charge which produces it, and the charge which produces it is called source charge. Is the property of source charge. It does not depend on the other charge which you are keeping to feel the force. Okay, so source charge, and of course, and it also will depend on distance from the charge, distance from the source charge. Yes or no? Like how much fragrance you will get will depend on how far you are, from the my from my body, right? Because I am the source of that fragrance. Yes, okay, so this is very important. Okay, so now question is, fine sir, very nice, okay, nice definition, we understood everything, but how do we measure electric field? How do we measure? In physics, see students, Just because you are able to define, it doesn't mean you have understood the concept. Okay, you must be able to uh, measure the electric field. Okay, if you are not able to measure it, then it is of no use. So in physics we always consider quantities which can be measured. Okay, so let us now see how to measure electric field at a point. So when you measure electric field, we also call that quantity electric field intensity, but most of the time everybody calls it electric field only. Okay, so now tell me, what do you need in order to have electric field? You need just source charge. That's it. And of course you need space wherever you want electric field. So let us say I have some source charge. Source charge. Why I made like this funny shape? Because it can be point charge, it can be ring charge, it can be spherical charge, it can be uh, sheet of charge, it can be any kind of charge. Okay, so imagine there is a source charge. Now, what I told, this charge will create electric field in the surrounding space. So I want to know what is the electric field at some distance r from this source charge at a point P. So P is called observation point. Why? Because this is the point where we will observe the electric field produced by this charge. Okay. So I want electric field at this point due to this charge. Okay. So definition and all we have understood, but what about formula? How do we calculate electric field? So for that, you have to do this. You have to keep here another charge, Q naught. And that Q naught we are going to say test charge. What charge? Test charge. Why we are calling it test charge? Because using this Q naught we will test what is the electric field here. Understood? Okay. So we will keep this Q naught here, and by definition this Q naught, this test charge is always positive. Okay, positive test charge. See why it should be positive only if you are thinking, then see I have one source charge here, one source charge, one source charge. Imagine I have many source charge and I want electric field due to this source charge. I want electric field due to that source charge. So to measure the electric field produced by different source charge, I must measure same kind of I must use same kind of test charge. The one that you are using to test, that should be common for everybody, so that you can decide, okay, this source charge has more electric field, this source charge has less electric field, isn't it? If I want to know how you all performed in exam, then the question paper which is given to test you must be common. So that way we have decided positive test charge, common for everything. Okay, so what you do, you put here a test charge Q naught and find the force which this test charge, when you keep it here, will feel because of this source charge. So what is this force? Force on test charge because due to source charge. Okay, once you find the force on this test charge by this source charge, then what you do, divide that by test charge, and that is the definition of electric field at point P. However, there should be a condition, and the condition is this Q naught should be tending to 0. Tending to 0 means what? The value of this Q naught should be extremely small. Why? Let us think. See students, our job was to find what? Here is a source charge. Okay, I want electric field here at some point. That electric field should depend on whom I told, only the source charge. Whether you keep another charge or not, it doesn't matter. Understood? So it is like saying you are in a classroom, you are doing something in my absence. Okay, I want to know what you are doing when you are alone. Okay, now if I come suddenly like this in the class, okay, if I show you my full power, then you will be like very quiet and silent in the class. Yes or no? So I will not be able to, my effect on you was so large that your behavior only changed. And that is not what I want. I want to know what kind of behavior you have, okay, when you are alone. So in that case, what I should do, I should very quietly come, no, so my measurement should be very weak so that it doesn't affect your behavior. Understood? I have to come only, no, there is no way I can find your behavior without observing. But my observation, the act of observation, whatever act I am doing to observe your behavior, should not be extremely large. Then your behavior will not be as it was when you were alone. And my aim was to find how you behave when you are alone. Similarly, our aim is to find, see, the question was what? Let us go back once. The question was, here is a source charge and I want to know electric field at this point. P is just a point. Points are everywhere in the space, right? Okay. So that's the question. See, there is no other charges here. I'm not putting any charge here. But how will I find the effect of this source charge in the surrounding space? Okay, effect you cannot find on nothing, right? So what we do, we keep here a test charge. And the value of the test charge, what I told, should be extremely small. Why? So that that test charge will not affect the distribution of this charge. See, imagine this charge is like this. Now, if your test charge Q naught is very strong, very high positive, then this positive will push all the positive this side. Yes or no? So the distribution will change. So whatever you are measuring is not what you wanted to measure. You wanted to measure the electric field here due to this charge, not due to this distribution, which has been affected by the presence of this charge. So that's why we want this Q naught, whatever charge we keep here, we want that to be extremely small. Okay. So we measure the force, that force on a test charge which is extremely small, and then we divide by the test charge. Okay, and what I told, this test charge should be extremely small. So I hope you understood why the test charge value should be extremely small, so that it doesn't affect the distribution of source charge. Okay, now some of you are thinking, I know, why are we dividing by Q naught, sir? Multiply by Q naught. Add to we cannot do, because add we only do similar quantities, right? 5 mangoes plus 4 mangoes, 9 mangoes. 5 mangoes plus 3 apples is nonsense. So you cannot add. But why divide only? Think about this. I told you what? I told you the whatever is this electric field should depend on only which charge? Source charge. Now in the force, go back to Coulomb's law. Imagine this is some point charge. Imagine some point charge here. So in the force, there will be this Q naught also, right? 1 by 4 pi epsilon naught. This Q, whatever you will keep here. And that Q was what? Q naught. And when I divide by Q naught, what will happen? Q naught will cancel. And therefore, electric field will not depend on Q naught. It will only depend on source charge. Right now, I know it looks like it depends on Q naught. It looks like it is inversely proportional to Q naught. But understand the fact that this force, in the formula of this force, there will be Q naught. So when you substitute that formula, Q naught will cancel. And that is exactly our next topic. But before that, let us talk about units. So what is the SI unit of electric field? So SI unit of electric field is how much? This is force, so Newton. This is charge, so per Coulomb, which we write Newton per Coulomb. Okay. Now let us talk about dimension. You can try yourself at home. We have discussed already before dimensions of charge, right? A into T. So since you have now understood what is the formula for electric field or how to find electric field due to any source charge. So electric field due to any source charge is force experienced by a uh, or you can say force per unit charge also, because you are dividing with Q naught. So when you divide by Q naught, you can also call it per unit charge, right? When you say rupees 1000 divided by 10 apples, rupees 100 by 10 apples, then what will be the answer? Rupees 10. So once you divide rupees 100 by 10 apples, then what do you get? This is price of one apple. So this is force on 1 coulomb because you have divided by Q naught. Understood? So this is force on 1 coulomb. What is this? This is force on Q naught. Right? You remember, right? I wrote here also. This is force on Q naught. Once you divide by Q naught, what will be this? Force on 1 coulomb. Matlab force per unit charge. For example, here this is price of 10 apples. This is price of 10 apples. This is price of 1 apple. So similarly, this is force on Q naught. This is force on 1 coulomb of Q naught or 1 coulomb of charge. And of course, the limit Q naught tends to 0. So this definition you remember. So now let us try to do the next topic, which comes for 3 marks in your board exam, and that is electric field due to point charge. I told you electric field is produced by source charge. The source charge can be any kind of charge, but let us start with point charge. Okay. So let's say I have a point charge plus Q, which is my source charge, plus let me take. And my question is, I want to know what is electric field at a distance R. Where? At this point. And let us make it a vector R bar. Then you can say here there is R cap. Last class also we have discussed. Okay, while writing Coulomb's law. Now, if you want electric field here, this is point, okay, not charge, point. Now, if you want electric field here, what is the concept? First, find force on a test charge Q naught if you keep it here. See, you don't have to keep it. Just imagine, just imagine if you put Q naught here. What will be the force on Q naught? I can use Coulomb's law because this is point charge. So 1 by 4 pi epsilon naught Q naught by distance between them magnitude is R square into R cap. Why R cap? Because I am writing vector form. Okay. Once I know the force, what is electric field at this point P? It is the force experienced by Q naught due to this Q, but this Q is capital Q. So let me write here capital Q per test charge. Right? So when you do that, what will happen? Substitute. So if you substitute this force here, Q naught will cancel as I told you before. So the electric field will be 1 by 4 pi epsilon naught Q by R square R cap. So this is the formula for electric field due to point source charge. Due to point source charge. Is it clear? Okay. So just make a note of this. Now students, if I want only the magnitude, then I will not put bar, right? So if I take magnitude both the sides, I will get 1 by 4 pi epsilon naught source charge and distance square. So this formula clearly means that the electric field only depends on the source charge. So don't write by mistake Q1, Q2. That you write in the formula of force. Why? Because whenever you speak about force, how 100 times I have told, force is always on something by something. So whenever you write force, there should be always two charges, Q1, Q2. on one charge by another charge. But when you write electric field, there will only be your source charge. Understood? So this is the electric field produced by this source charge. At what distance from the source charge? R. This is R. At which point? P. So electric field is always calculated at a point. And what is this R? How should I say R now? Can I say distance between two charges? There is no charge here. The job of Q naught was just to measure the electric field. Once we simplify, we see that Q naught will cancel, no Q naught. So there should be, in order to have this electric field, you don't need Q naught here. See, where is Q naught in the formula? It got cancelled. That's why we have done all this. Okay. So what is R now? Distance between, don't say two charges, distance between source charge and observation point. Observation point. So it is distance between source charge and observation point. Fine. Now we have seen the magnitude. What about direction of electric field? So let us say your source charge is positive. Then at this point, at a distance r, okay, you know how to write the magnitude, right? 1 by 4 pi epsilon naught q by r square, only q. But if you want direction, then you have to go to the vector formula for electric field, force experienced by a positive test charge. Okay, you need positive test charge. So since if I keep here a test charge, positive test charge, where will be the force? Repulsive. And if force is this way, electric field will be also that way because it is equal here. So electric field due to plus charge will be always away from the plus charge. Away from the plus source charge. Okay. Do not use the word repulsive when I ask in what direction is electric field. If I ask, don't say repulsive like that. That you say for force. Force is repulsive or attractive. Electric field due to positive charge will be away from the positive charge along the line joining the charge and the point. This is just a point. Similarly, if your charge is negative at a distance r, where will be electric field? Towards. Why? Because if I put here this Q naught, the force will be attractive. So if force will be attractive, electric field will be towards this negative charge. So try to remember this, students. Electric field is away from positive charge at a point, and electric field is towards negative charge at a point. So electric field is towards negative source charge. Okay, so try to remember this concept. Okay, now let us talk about what will happen if there are multiple point charges. Then you know what to do. Just apply superposition principle. So multiple electric field due to multiple point charges. Okay, so let us say I have Q1 source charge, Q2 source charge. Let's take two charges, no problem. Okay, one more we'll take. Okay, Q3 source charge. Now somebody says find electric field at this point. This is your observation point. Again and again and again I'm saying electric field is always calculated at a point due to source charge. This time you have three source charge. Then how to find electric field? Right? Electric is the region. No, it's a region. So electric field is always calculated at a point. So this is in the region of this also. This is in the region of this also. This is in the region of this also. So all of them will contribute. So you have to use superposition principle. So let us make it interesting. No, let us make one of the charge minus. What is there? Right? You try for positive. It will be easier. So due to this Q1, electric field will be positive, means where it will be away along this line. This is your E1. Right, students? Okay. And what about electric field due to Q2? It will be positive, so it will be away E2. Okay. And due to minus Q3, it will be towards. So this arrow, vectors are represented by arrows, okay? So this is your E3. So then you calculate the magnitude. You know the magnitude 1 by 4 pi epsilon naught q by r square. Once you know the magnitude, then you use vector addition. Add these two, whatever answer will come, add with this one. And we have done, we will be doing more problems later. So I hope, so at the end what I should write, resultant electric field at P will be electric field due to Q1 plus due to Q2 plus due to Q3. So this is your superposition principle. Okay, superposition principle. Super. Okay. Uh, Try for these two charges. Think here Q1 is there and here Q2 is there, and tell me electric field at this point. Okay, try draw a diagram and show me the resultant. So pause the video and try. Okay. So if you have tried, due to this plus Q1, electric field will be away E1 bar, right? Yes or no? This video. Let me just adjust the camera. Oh, yeah. So sorry for this. Okay. Yeah. So this E1 is due to Q1 and due to Q2 it will be here, right? E2. Right? And once you know, since I have given you only two, then you can draw parallelogram and this diagonal will give you the resultant electric field. And the formula of that you know already. Let us not waste time. Okay, root over E1 square plus E2 square plus 2 E1 E2 cos of this angle. Okay, so like this you have to use superposition principle to find electric field due to multiple point charges. You can write formula also here, 1 by 4 pi epsilon naught q1 by this r square, but you write r cap. So for this you write r1 cap, for this you write r2 cap, for this you write r3 cap or minus r3 cap, depending on your wish. If you write r cap here, then write r cap only. If you write r cap here, then write minus r cap, because this electric field is this side. But this much if you write, it is enough. Okay. Okay, so we have learned how to find electric field due to multiple point charges also. Now, till now students, we have spoken about only point charge, right? But what if my charge is not point, but it is distribution of charge, like a ring or line of charge or spherical charge? So in that case also we can use superposition principle. But you know that if I have a line charge, I cannot consider that line as points, because then there will be how many points? Infinite points. Yes or no? So the trick is this. So now let us discuss quickly continuous charge distribution. So if you have continuous charge distribution, okay, so if I rub charge on a scale, then the charge will be continuously distributed. Okay, so in that case there may be three kinds of distribution. So one is called line distribution. So imagine in a line charge is distributed. In a line charge is distributed. Then we define something called linear charge density. In exam it comes for to define. Okay, So what is linear charge density? The symbol is lambda. It means you take a small part of this, length of this is, let us say, dl, and charge on this small part is dq. I hope you know from mathematics or from first PU differentiation. The dx, if I write, it represents a small x or a small change in x or a small change in x. Okay. So here lambda means dq, charge, divided by length dl. So basically it is charge per unit length. Okay. If the distribution is uniform, if the distribution is uniform, then you can also write this dq by dl as total charge by total length. Total charge by total length, right? So if you have water in a bucket, and you know density of water is uniform, density of water is constant. So in that case, it doesn't matter whether you take the whole mass of water and divide by the whole volume, or you take a cup of mass of water and divide by cup of volume. Answer will be 1000 kg per meter cube always. So if the distribution is uniform, matlab if the density is uniform, linear charge density is uniform, then it doesn't matter whether you take small charge divided by small length or total charge divided by total length. It doesn't matter. It is the same thing. Okay. If it is uniform, if it is not uniform, then you have to use only this. Okay, then it means here this lambda will be different, here this lambda will be different, depending on how much dq is there in that small length. But if it is uniform, then you can write like this. So this is your linear charge density. Second thing is sometimes your charge will be spread on a surface. So this is surface. So when charge is spread on a surface, we talk about something called surface charge density. Symbol that we use is sigma. Greek letter sigma, small letter. Okay. So this is capital sigma, this is small sigma. So small sigma is equal to, how do you define? Take a small area, dA, and whatever charge this area has, dq, you divide. So it's dq by dA. So it is charge per unit area. What is the unit of this? Coulomb per meter. What is the unit of this? Coulomb per meter square. Coulomb per meter square. And if it is uniform, then you can also write total charge by total area. If it is uniform, same thing you can write here. Okay, if it is uniform distribution, then you can also write sigma, which is surface charge density, as total charge by total area. Then the third thing which we have is the charge is neither on a line nor in a surface, but the charge is spread in a volume. So in that case, you have some volume, 3D volume, okay, like this. So charge is everywhere. Okay, so if charge is in a space, then we define volume charge density. Volume charge density. Okay, and how do you define this? Symbol we use rho. You take some small volume here, dv, and calculate the charge in that dv, which is dq. Then this is dq by dv. If it is uniform, same thing. If it is uniform, it matlab density is uniform, then you can also write same density as total charge by total volume. Okay, it's like if you run uniformly, if you run uniformly, whether you divide small distance by small time or total distance by total time, you will get always same velocity, right? If you move uniformly. If your velocity is constant, then whether you write small distance by small time or total distance by total time, you will get same answer. So if it is uniform distribution, density is uniform, then you can use either this or this. Fine. So this is how first we have learned how to write charge for linear charge and surface charge and volume charge distribution. So now how will we calculate electric field due to continuous distribution of charge? So for entrance exam this is very important. Electric field due to continuous distribution of charge. So imagine I have some distribution of charge and I want electric field at some distance. Here I want due to this distribution. Now you cannot use this formula. You cannot use this formula. Why? Because this is not a point charge. This formula came from where? Coulomb's law. Right? I used Coulomb's law to derive this formula. Go back and check once. So that was done for only point charge. So now your charge is not a point. Then what to do? Then here comes your knowledge of integration, which we have studied in first PU, and in mathematics they will teach you more in second PU. So what is the idea? The idea is this whole charge cannot be considered as point, but if you take a extremely small volume, what volume? Extremely small, dV. So once I write d, no, it always means infinitesimally small. Infinitesimally small means the volume tends to 0. So if I take an extremely small volume whose size tends to 0, then it means I can consider this almost like a point charge. And whatever charge it has, let us say dq. Yes or no, students? So then electric field due to dq charge. Now since this is dq charge, since this is dq charge, this is like a what charge now? Point charge. So for point charge I can use this formula which I wrote before. So I can write electric field now as dE. Why dE? Because it is small electric field. Small in the sense it is produced by a small part of the distribution, not the total electric field. So I am writing dE. So that will be, what is the formula for point charge? 1 by 4 pi epsilon naught. Charge is dq. This is the source charge divided by distance of source charge from the point. Let us say r. R square into r cap. Okay. Unit vector is r cap. Then to find the total electric field, net electric field, what you do? Integrate dE. मतलब integrate 1 by 4 pi epsilon naught dq by r square r cap, so that you cover all dv's or write all dq's. So what is the meaning of this all dq's? So this all dq's means this integration should be done so that you cover this dq, this dq, this dq, this dq, every dq in this distribution. So basically I am saying superposition principle only. So this continuous charge, we are dividing it into small pieces. Each piece is so small that I can take it like a point charge. So I can use the formula for point charge, electric field due to point charge, when I consider a small piece only, and the charge on the small piece I wrote how much? dq. Then to find total electric field, what you do? Vector sum. But since it is continuous, instead of using summation we are using integration. Okay, so this integration we will be doing after some time later. So this is, so in board syllabus up to this you have to do. Now for entrance syllabus we have to find electric field due to line charge. Okay, then we have to take for spherical charge, sheet of charge. So many kinds of distribution of charge we have to take later. Okay, so I hope till now whatever I have explained is clear. So let us just revise once. Okay, so electric field is the property of source charge. Basically, it is the region where another charge will feel a force. So electric field is the region surrounding the source charge where another charge will feel a force. And now we don't say, basically we don't say this Q exerts force on this Q naught. Directly we don't say. We say this Q creates electric field. And that electric field will exert force on this Q. So students, tell me this thing, okay? Suppose you know electric field at some point. Suppose you know electric field at some point due to some source charge which I am not showing to you. There is some source charge somewhere. And that source charge I am saying creates this much electric field at this point. Now you tell, if I keep here a charge Q, okay? If I keep a charge Q, what would be the force on that Q? Now some of you are saying 1 by 4 pi epsilon naught, correct? No? No, because I did not tell you the source charge only. I did not tell you the source charge is point charge. So how can you say 1 by 4 pi epsilon naught? Yes or no? So go back and think, what is actually E? E was force per unit charge when a small infinitesimal charge is kept at that point. So that is how E was measured. No, E was basically force on 1 coulomb due to some source charge. So once you know that E is force on 1 coulomb, now don't say, "Arey sir, it was force on Q naught coulomb." Arey, this was force on Q naught coulomb. Once you divide by Q naught, that will become what? Force on 1 coulomb, right? So if this is 1000, this is 10 apples. This is not price of 1 apple. This is price of 1 apple. Understood? So what is E? Force on 1 coulomb. So what will be force on 2 coulomb? Tell me. 2 into E, force on 6 microcoulomb. 6 microcoulomb into E. So what will be force on Q coulomb? Q into E. So make sure you remember this, very important. If Q is positive, whatever charge you keep here, then force will be in the direction of electric field. Force will be in the direction of electric field. And if Q is negative, if there is a minus sign, what does it mean? This vector is opposite to this vector. So force will be opposite to electric field. Okay? Excuse me. So this is something which I wanted you to know. So let us see some learning exercise now, so that whatever we have learned till now, it will be, the ideas will sink. So if you see the learning exercise, question number 1. Okay. So this is learning exercise 3, I think. Okay. So please check. I don't have the material today. Okay. So I have noted down the questions. So learning exercise 3, I think. So question number 1 says, a charge 2 nanocoulomb. A charge 2 nanocoulomb experiences a force of it. This one is experiencing the force. Okay. So this experiences a force of 10 Newton. So question is, what is the electric field at that point? So they want electric field at this point. Okay. So how do you define electric field? So you know that this force, right, is experienced by this charge. Why? Because at this point there must have been some electric field due to what kind of charge? Due to some source charge which we don't know also. We don't have to know also in this question because they have given you the force. So force formula just now I told Q into E. And this Q is the charge which feels the force or uh, which produces the electric field. This Q is the charge which feels the force, right? Just now I explained. E is due to another charge, which they have not mentioned in the question. So force is 10 Newton. The charge which feels the force is 2 nanocoulomb, means 2 into 10 power minus 9 into E. So what is E? 10 divided by 2 into 10 power minus 9, which is 5 into 10 power plus 9. Unit will be what? Force by charge. Newton per coulomb. Now they are asking, is this electric field due to 2 nanocoulomb? No, 2 nanocoulomb is feeling the force. Right, students? So that is not, it is like your test charge basically. So this is like your test charge. It is not the charge which is producing the electric field. So answer is no. Second part, no. The electric field is not due to this charge. This is the one which is feeling the force. Electric field is produced by the source charge, right? Which they have not mentioned. So basically, the beauty of electric field, no students, is this. At any point, if you know electric field, if somebody says that electric field here is E, then it means you know what will be the force on 1 coulomb. That will be this itself. Because that is the definition of electric field, force per unit charge. So if I tell you at this point there is electric field, then obviously you know there is source charge somewhere. You know there is source charge somewhere which is producing this electric field. Yes or no? But what is the meaning of this electric field? Again, force experienced by a unit positive charge kept here. So if I don't put unit charge, but I put 2 unit charge, then it will be how much? 2 into E. If I put Q charge, what will be the force on the Q charge? Q into E, because this is force on unit charge. Try to memorize this concept, okay? And this E is not due to this Q. This Q is kept here in order to feel the force. So if you want to feel a force, you need another charge, right? So that charge is this Q. This E is produced by the source charge. So keep that in your memory. Okay. So once we are done with this, okay, let us see the next question now. So the next question is question number 2. Very simple question. There is a charge 10 microcoulomb at a distance of 3 meter from the charge. They want electric field. Now this charge is given to be point charge. And once you know it is point charge, what is the formula for electric field? Magnitude, let us calculate. 1 by 4 pi epsilon naught, the value of the source charge divided by distance from the source charge and observation point, r square. Okay. Now what is this value? 9 into 10 power 9. What is the source charge? 10 microcoulomb. 10 power minus 6. R is 3. So r square will be 9. So this 9 and this 9 will cancel. 10 to the power 9 plus 1, 10. 10 minus 6, 4. Newton per coulomb. Okay. And direction will be where? Since the source charge is positive, direction will be where? At this point, away from the plus charge. So this is the direction. This is the magnitude. Third question says, what if the sign of 10 microcoulomb charge is negative? So first you make a note of this. So in the third question, if this charge is negative, how will the answer change, they are asking. Will the magnitude change? No, when you write magnitude, what do you write? Modulus of charge you write, right? So that will be this only. So answer will be same, but direction will be different, right? So for negative charge, how will we show the electric field? For negative charge, electric field is towards. So students, my advice is this. This is new concept, right? So my advice is try to revise whatever I have done, and now it is very easy to revise. Just go back, right? In the video you go back, see the video and try to revise whatever I have done again and again. So the more you hear, believe me, the more you will understand. Okay, and finally, once we have completed this learning exercise, now I will tell you why electric field is real, why it must exist. So let us discuss. Okay, concentrate on this one. So this is physical meaning of electric field. Don't worry, in board exam they will not ask this. So just for the sake of enjoyment, you understand. For the sake of learning, for the sake of knowledge, you see. Here I keep a charge plus q. At some distance r, I keep a charge small q. What does Coulomb say? Coulomb say this will feel a force 1 by 4 pi epsilon naught q by r square. Yes or no? Yes or no? This is the Coulomb's law because I have considered point charge. Now listen carefully. Suppose I move this charge and I keep this charge here. This distance will change. So the force will change. Yes or no? Force will change if I change the distance. Now, if I move the charge, I move this charge, move the source charge, if I move charge Q at 10 p.m. or a.m. What's the time now? 3. I don't know the time. I think it's 3 something. Okay. Anyways, don't worry about the time. Suppose I move this charge at 10 a.m. According to Coulomb's law, at what time this will feel different force? Because this force will, the moment you change R, this F will change or not? It will change, na? So, if I move this charge at 10 o'clock, at what time this will feel different force? This charge will feel different force. That time only, at 10 a.m. only. Understood? Because the moment this changes, this will change. Equality is there, no? You may take time to calculate, but that doesn't mean this will take time, right? So 2 into 4, 2 into 2 is 4, 2 into 3 is that moment only. The moment you make 2, 3, answer will be 6 that moment only, right? So according to Coulomb's law, if you move this charge now, this will feel a different force now. That means the cause at what time, the cause is this, right? The effect is this. So I am moving, that is the cause. This is feeling a different force, that is the effect. So if the cause is at 10 o'clock, effect is also at what time? Effect is also at 10 o'clock. But this is impossible according to Einstein's theory of relativity. According to Einstein's theory, nothing in this world, no information, no objects, nothing can travel faster than speed of light. So if the cause here happens at 10 o'clock and effect also happens at 10 o'clock, that means this information, which information, that hey, I have changed, I have moved, you should feel different force, that information has to travel faster than speed of light because it has to happen at the same time. Cause is happening here, right? Effect is happening here. If both happens at 10 o'clock, it means whatever information has to come, it has to come at zero time because there is no time. And to cover to cover that distance in zero time, the information has to travel with what speed? Infinite. But nothing can travel faster than speed of light. Forget about having infinite speed. You can't even cross speed of light. That means this formula, when you write, though it is correct when the charges are at rest, that's why we say that this formula is true when charges are at rest. The moment you move the charge, then this will feel a different force, and that force will not be felt at the same time. Okay, so now comes the use of electric field. Understood, students? So what we say is, this capital Q is there, this small q is there. We say there is a field everywhere, right? There is a field. You cannot touch it, you cannot smell it, okay? But there is a field. When this charge is at rest, this field is also at not rest. I cannot say because this field is not object, right? So I cannot say field is at rest, but the value of the field is constant in magnitude and direction. So whatever electric field is here, that will be fixed because of this charge, and because of and at this point, at this point, at this point, at every point, the electric field produced by this charge will be fixed in magnitude and direction. So it's like saying there is water and my finger is on the surface of the water at rest. Then water is also static. So when the charge is at rest, the field here is static field. However, once this charge moves, once my finger moves in the water, they creates a ripples. So similarly, when you move this charge, this field will start changing, and these changes in the field will take time to reach from here to here, and then this charge will feel a different force. So if you bring field concept, then if you move this at 10 o'clock, this will not feel different force at 10 o'clock. Why? Because the changes in the electric field will travel with a speed, and that speed is 3 into 10 to the power 8 meter per second. And that's why the field concept is very useful. Without the field concept, it would mean that if this is moving at 10, this will also feel a different force at 10. But that is not the situation, because you have to keep in mind that no information can travel faster than speed of light. So keep this in mind. This charge is at rest, this charge is at rest, there is this much force. However, the way we say now is this charge creates electric field 1 by 4 pi epsilon naught q by r square, right? So if you have a point charge capital Q at a distance r, what is the electric field here? Electric field I'm asking. So 1 by 4 pi epsilon naught, electric field contains only source charge by r square. Right? I told you this. Now if you keep here a charge Q, it will feel a force Q into E. Remember I told you this before? So because E means what? Force on 1 coulomb. So if you put Q coulomb, force will be Q into E. And if you substitute this E, then you will get Coulomb's law back. But the beauty of, right, this is Coulomb's law only, right, r squared. But the beauty of this explains that there is a way in which this feels a force because of this. It is not direct. So this creates electric field, and that electric field exerts force. And when this charge moves, then the changes in the electric field will take time to reach from one place to the other place. Because this changes in electric field is what we call electromagnetic waves.